Hi, I'm Begum Genc. I'm a postdoctoral researcher working at University College Cork. In this video, I will present you our application paper with Barry O'Sullivan that's on solving the examination timetabling problem at University College Cork by using a two-phase constraint programming model. In the video, I will first talk about the problem definition and some constraints of the problem, and then I will present you our proposed two-phase constraint programming model in detail, then provide a discussion of the decomposed models, and I will conclude my presentation by showing some empirical results. The examination timetabling problem in general is about finding a suitable time slot and a venue for each examination by respecting the hard and soft constraints given by the institution. So in this work, because it's a real-world problem from UCC, it's not very easy or it's not really possible to relax the hard constraints. So the problem becomes a bit difficult when you are dealing with the real-world problem. And when we look at the problem size, we have a fairly large model, and our aim is to build an inclusive and fair model for the students. So we want to increase the fairness measures, and we are including all the students that have some special needs in our model. So the special needs students may be students with some requests such as they must sit an exam on their own in a separate venue or in a shared venue or in a lab, but they must be seated away from the main groups. And this is how our model looks like in general. In phase 1, we are assigning each exam into we are assigning each exam a time slot, and then in phase 2, we are assigning each exam into a room during the given time slot. And both of our phases are heavily relying on the bin packing constraints. Especially in the second phase, we are dealing with the bin packing with fragmentable items problem, which is interesting because we noticed that the constraint programming community have paid little attention to this problem so far. And this is how our results look like. We are significantly improving the UCC's current schedule. And we think that this work is especially important at the moment because due to the pandemic-related constraints, such as the social distancing measures, it's not practical for institutes to hold exams without allowing split exams anymore. So the institutes can tailor this model to their needs, and they can figure out what is the minimum number of rooms required for them in order to hold physical exams in the institutes. So thank you for listening to me. In the rest of this presentation, I will talk about the details of our work. So now I will talk in more detail about the examination timetabling problem. As I said before, it's about finding a venue and a time slot for each examination by definitely satisfying the hard constraints and violating the soft constraints as little as possible. And it's a widely studied problem as it emerges in every institute. So in literature, we see some graph-based algorithms, some exact methods like MIP models, and some heuristic approaches like local search or population-based ones, etc. And there was also some constraint programming approaches, but they were using constraint programming to construct an initial solution, and then they were improving the solution by using some heuristic methods. So as I said, there are already some exact methods like MIP models, but when we try to tailor those models to UCC's needs, we realize that due to the split constraints, the exam splits, the model becomes very heavy, and this stage is very costly, and we cannot really obtain a solution in time. Therefore, we needed to construct this decomposed model. And now this is a more visual representation of the problem. We have some time slots, and we have some rooms available during each time slot, and the goal is to find a suitable room and time slot pair for each examination. So this is the case with no exam splits. And if the exams are allowed to be split, then we can see the same exam being sit in more than one venue during the same time slot. And the way that we handle this problem is that we treat each time slot as a bin, and we say that the capacity of the bins are equal to the total number of seats available in the available rooms during that time slot. And we say that our items corresponds to exams, and we pack the exams into the bins, which are time slots. Then in the second phase, we are decomposing the problem further because we notice that our days are occurring independent from each other. And then for each day, we have three time slots, one morning session and two afternoon sessions. And in each time slot, we have a number of rooms, and we are treating each of these rooms as our bins, and our items are again our exams, and we are packing the exams into these rooms. And we repeat the same thing for each day by allowing the exam splits. And we are making use of a very common structure called as conflict graph. In conflict graph, each vertex corresponds to an examination, and there exists an edge between two exams if and only if there is at least one student that needs to sit both of the exams. And the weight on an edge indicates the total number of students that are sitting both of the exams. Now I will go into the details of our phase 1 model. As I said, we are making use of the global constraint for bin packing that has been designed by Shaw, and we are repeating the same bin packing constraint for each of our groups. So we are packing each main group student into the seats available for main groups, and each separate, so let's call them as tags. SPR tag corresponds to a special need group with separate room, and SHR corresponds to another special need group and lab as well. So we are packing the students from each group into the seats available during each time slot. And by doing this, by the way, in constraint 1, we are making sure that each student has definitely a seat allocated for himself or herself. And in constraint 2, we are imposing the duration constraint, and we are saying that an exam occurs during a time slot which has at least the same duration as the exam. Then we are using the all different global constraint for saying that each exam that is conflicting with each other cannot be set during the same time slot. So their time slots must be different, so that a student is not required to sit more than one exam at the same time. Then all equal constraint for scheduling the exams that needs to be co-scheduled. Then we are using some inequality constraints. This stage is very straightforward. If an exam needs to be scheduled before and after a specific time slot, or should not be scheduled during some time slot, then we use the inequality constraints. And we have three main soft constraints. UCC says that a student should not sit more than one examination per day, or a student should not sit back-to-back exams, or a student should not sit more than one examination per any 2 days. And they have some priorities over these soft constraints, which we model using different coefficients, penalty coefficients in the objective function. And in our next constraint, UCC says that students are not allowed to sit more than 270-minute exams in total of over any 2 consecutive days. And there's also a time slot penalty associated with time slots, which means that some time slots are less preferred to some other ones. And what we do is that we are penalizing a time slot by using some coefficient, and also the total number of students that are scheduled an exam during that time slot. And we are accepting each exam with more than 100 students as a large exam, and ideally we want all the large exams to be scheduled during the early time slots as much as possible. Then our objective function is a weighted sum of all the violations of the soft constraints, and we want to minimize the total violations. Then our phase 2 model is pretty similar to the phase 1 model in the sense that we are making use of the bin packing constraint to pack groups of students into groups of venues by respecting their special need tags or no tags. And to capture the bin packing with fragmentable items problem, we are making use of some very straightforward modeling approach here, but there exists some MIP formulation, some decomposition methods in the literature, and also some heuristic approaches. So there is room for improvement for this constraint in our phase 2. And we are repeatedly using this constraint to pack the students into the venues. Then by using constraint 17, we are imposing the no mixed duration constraint, which is a general constraint for examination timetabling problems, which states that it's allowed to sit more than one exam in a venue at the same time, but the only rule is that the exams must have the same duration. Then we are using constraint 18 to keep track of the number of rooms in use during the examination period. This is mainly for constraint 19. In constraint 19, we are imposing each exam to be held in at most 2 different venues at the same time. This is coming from a solution from Shahnai. He is saying that his observation is that there always exists an optimal solution to bin packing with fragmentable items problem, which is primitive. And a primitive solution, as part of it, it says that each item is fragmented at most once. So we're imposing the constraint 19 to limit our sort space. Then by using constraint 20, we are imposing the different campus constraint. It says here that if a student is sitting more than one exam during the same day, then both of those exams must be placed into a venue in the same campus. So a student is not allowed to travel between the campuses during the day for examinations. And then constraint 21 says that if an exam is split to multiple venues, then these venues must be in the same campus as well. Then in constraint 22, we are counting the total number of rooms in use, and we are minimizing the total number of rooms in use as well as the exam splits for each group. However, we may end up with an infeasibility scenario by using our decomposed model. This is usually known as a drawback of the decomposed models. So our phase 1 model can return a feasible solution, but the phase 2 may return infeasibility when this initial solution is fed into the system. So assume here that this is a solution of returned by our phase 1 model, which says that there are 3 rooms available with capacities equal to 4, and R1 is located in a different campus. So here, exam 1, exam 2, exam 3, and exam 4, they all have 3 students in them, and these exams have 90-minute duration, whereas exam 4 has duration of 180 minutes. So the only solution that's possible for packing these exams into these rooms is by violating the mixed duration constraint and also by violating the exam split between different campuses constraint. So in order to get rid of this infeasibility scenario, we have some options such as relaxing some of the hard constraints, and these hard constraints here are the mixed duration, no mixed duration constraint, and the exam split to different campuses constraint. Or alternatively, if the model allows, if the data allows, then we can keep the maximum load of time slots to an acceptable level, which means that we do not fill the time slots. And this actually, we are making use of this approach in our model because by using this, we are making sure that we are respecting all the hard constraints, so we are not relaxing anything. And also, we are using less rooms in the model because the larger venues are more preferred to the smaller venues. and we are imposing this constraint here in our phase 1 model. And now we move on to the results. We implemented our model by using Choco Constraint Solver, and we have made some tests by using the built-in search strategies in Choco Solver. For phase 1, we tried these 4 different strategies. An interesting thing is that by using any of the strategies, we were able to find an initial solution in under 10 seconds. And when we compare these initial solutions quality-wise with the UCC's existing schedule, we have realized that these initial solutions are still much better solutions when compared to the existing one. And then when we look at the model in general, activity-based search was able to find the solution that provides the lowest objective value. Therefore, we have selected activity search as our main strategy. And by the way, for each solution found by our search strategies, we made a little test about checking their feasibility. So in total, for instance, activity search have found 5 solutions in total, and weighted degree, for instance, it found 11, and etc. And all the solutions found, they were all feasible. And we did this check by running our phase 2 algorithm subsequently after each solution by using a next fit strategy. And by doing this, we were able to tell on the average in about 1 second to say if this solution can provide a feasible solution for our second phase. So by looking at this, we can infer that our heuristic approach for handling the infeasibilities works in UCC's case. And for phase 2, we are using again 4 different built-in strategies. But now in this case, the strategy for assigning the first non-instantiated variable to its upper bound strategy was the only one that was able to find a solution for all 10 days. The other strategies failed to find solutions to some of the days among the 10 days. And therefore, we have selected this third strategy as our finalized strategy for our model. And when we compare the results obtained from our model with the UCC's existing schedule, we see some significant improvement, especially for the soft constraint violation. We are reducing the violations quite a lot. And we also noticed that UCC was violating some of the hard constraints, and our model is able to address all of or satisfy all the hard constraints. And in conclusion, we have reduced the work of administrative staff that was taking weeks to under 1 hour. And we have improved on the fairness measures and also for the requirement satisfaction measures. And one interesting thing that emanates from this work is that now with the current pandemic and the social distancing rules, when the if the institutes want to hold physical exams, then it's kind of mandatory now to have split exams. So the institutes can use this approach and use a similar model to tailor up to their needs, and they can decide on the minimum number of rooms that is required to be used when the exam splits are allowed for the physical examination sessions. And it's an interesting research direction to design a global constraint for the bin packing with fragmentable items problem. And actually we are continuing on this work, and some other decomposition techniques can be tried, such as the boundaries decomposition. And obviously, of course, if needed, some state-of-the-art heuristic methods can be tailored for comparison with our model for UCC's schedule. And thank you very much for listening to my presentation. If you have any further questions, I'm happy to answer them. Please direct them to my email address. Thank you.